APAB Calc. We're doing the last topic in 2.3, which is higher order derivatives. Okay, so before we do any of the actual calculations on this, we're going to talk about some notation because there are a lot of different ways to write the derivative of a function. So let's assume that we're starting with a function that we're either calling y or f of x, because that's usually the standard. I mean, it could be a g of x or an h of x, or it could be z is your dependent variable for some reason, or whatever, you know, or h for height or something. But in this case, let's just use y and f of x as like our test cases to show what this looks like. So we've already seen that the first derivative, we often use this thing called prime notation. So if I have a function y, its first derivative would often be written as y prime, right? Or if it were f of x, we'd often write it as f prime of x. But the other way that we can see this is in what we would consider dy dx notation, right? Which is sort of like a quotient notation, where the dy dx essentially means change in y over change in x, just like that little delta triangle that you're used to seeing. But the d represents a really, really small change in y and a really, really small change in x instead of the big delta y delta x. So y prime and dy dx mean exactly the same thing. F prime and d dx of that f of x, right? So the derivative, remember we've seen that notation before, that d dx tells you to take the derivative. So if you think about it that way, d dx with that y there means take the derivative of y, right? So differentiate y. When we get to second derivatives, and we're going to walk through how you actually calculate the second derivative after we go through this notation. But essentially, the second derivative is just what happens when you differentiate the first derivative. So to get from y to y prime, you differentiate. To get from y prime to y double prime, which is how we'd say this as y double prime, okay? You would differentiate. To get from y double prime to y triple prime, you would differentiate. And then after 3 primes, we usually don't see it as little hash marks anymore. We see it as the number, like the number 4, but in parentheses. So I do want to point out, and I have this in the bottom corner here, I'm not sure if you'll be able to see it over here right now, y to the 4th means y to the 4th power. Y to an exponent of 4 that's in parentheses means the 4th derivative of y. That's the difference. So a y with a 4 exponent means y to the 4th power, meaning y times y times y times y. A y with a 4 exponent in parentheses means the 4th derivative of y. And then if we wanted the nth derivative, so I could take like the millionth derivative, right? I could differentiate 1,000,000 times. And if I did that, I'd get a y with 1,000,000 up in this little parentheses. That would be the millionth derivative. And obviously, you're not going to be asked to do that unless it's a trick question, and we'll talk about that. Now, in the other notation, right, this quotient notation, what I want you to notice is that if you think about this d dx as the operation, then it makes sense why the squared is between the d and the y, because I want you to think about this as taking the second derivative of y. Well, d squared dx squared means derive twice of y. So it's d squared y dx squared. The squared goes between the d and the y on the top, right? And when you do the third derivative, you're going to see the same thing but with 3's, right? Because think about it this way. This is saying differentiate 3 times. The d dx is saying differentiate. So it's d dx, sorry, I'm trying to not cover the 3 on the bottom, d dx 3 times. So d dx both have 3's on them as a power of y. So that's why the y doesn't have the power. Same thing with 4, and down here you'll see d n y dx to the n, right? Because that's take the nth derivative of y, right? So the d and the dx both have that n power. If we go over to the f prime notation, right? So f prime is the first derivative, f double prime is the second, f triple prime is the third. And then we see the same pattern here where if we want the 4th derivative of f, we don't write it with 4 primes. We write a 4 with parentheses as that superscript, right? Same thing down here. I write a 4 with parentheses as that superscript. An n with parentheses as the superscript. So this means the nth derivative of f. That's going to come into play a lot when you get to Calc BC, because we talk a lot about behavior of things when n gets to be really, really big numbers, like as n approaches infinity when we get to Calc BC. So it's going to matter that you understand how to deal with these n's when you get there. The last column is basically the same as this d squared y dx squared, except it's d squared dx squared of f of x. It's the same notation. Again, if you can remember that d dx is essentially the action of taking the derivative. This is saying take the derivative twice of this f of x, and then 3 times, 4 times, n times. So what we're going to do here, and I'm going to inch this guy over a little bit so you can see, this is not example 1, this is just, or whatever example we'd be on, I think we'd be on 7. This is just to walk you through what I mean by differentiating the derivative. So I picked a really easy example. I picked x to the 6th. If I were to differentiate x to the 6th, I would get y prime, right? Or if you like it better, you could call it dy dx, right? If that makes you feel better, it's the same thing, okay? Same thing. And it's going to be a 6x to the 5th using the power rule, right? If I wanted to differentiate again, this would be d squared y dx squared. or y double prime, either of those, same thing, different notation, right? And that would be a 30, because the 5 drops down in front, so 30x to the 4th, right? And if I wanted to differentiate again, that would be y triple prime, or if you like this notation better, d cubed y dx cubed. I think most people like prime notation better, but it's up to you. And again, I would differentiate, so I'd bring the 4 down, so I'd get a 120x to the 3rd, so I'm kind of running out of space here. And if I wanted to differentiate the 4th time, again, that would be, if you want to write the other notation, it's d4y dx4, right? I would bring that 3 down, and I'd get a 360x squared, right? And again, it's a little bit crammed at the bottom. And obviously, I can't easily do the nth derivative of this, because the nth derivative is a derivative that I don't know what value. It's not the 5th or the 6th or the 7th. It's some derivative down the line. So that's the idea of this higher order differentiation. Most of the time, we're not going to care which of these notations you use. It's good to be comfortable with both. Some of you are going to naturally feel more comfortable with the prime notation. Some of you are going to prefer the quotient notation. It's up to you. It doesn't really matter. That's kind of the gist, right? And there will be times that it's more useful. In fact, we're going to see when we get to 2.5, which is 2 sections down the line, we're going to see that we want to use quotient notation. Sometimes we want to use dy dx notation sometimes. But for right now, it doesn't really matter which one you feel comfortable with. So we're going to go ahead and practice some examples where we differentiate and do higher order derivatives. And then I'm going to give you a couple trick questions, because I said earlier that I wouldn't ask you for like the millionth derivative of something unless it was a trick question. And I'm going to walk you through how there could be some trick questions down the line that I could ask you for like the 100th derivative or the 205th derivative, and you would be able to find it without actually sitting there and differentiating 205 times, okay? So we'll do that in the next video. So for this video, again, we just quick introduction to the notation of these higher order derivatives.